Here's something that should fundamentally disturb you about the current state of physics. We've spent the last 100 years, arguably the most productive century in the history of science, developing increasingly sophisticated theories, building bigger and more expensive experiments, training generation after generation of brilliant physicists, and at the end of it all, we've discovered that we understand about 5% of the universe. 5%. That's not a metaphor. That's not me being dramatic. That's the actual number that comes out of our best observations and calculations. The other 95%, we have no idea what it is. None. We've given it names, dark matter, dark energy, but those are just labels for our ignorance. It's like a doctor telling you that 95% of your body is made of something called mysterious substance, and we don't know what it does, how it works, or why it's there. You'd be terrified. You'd demand answers. You'd wonder how medical science could possibly claim to understand human health while being completely ignorant about 95% of what you're made of. And yet, that's exactly where we are with cosmology. We're studying a universe that is overwhelmingly composed of things we cannot see, cannot detect directly, and do not understand. And somehow, we're supposed to act like this is normal, like this is just how science works. Well, it's not normal. It's embarrassing. And it's absolutely fascinating, because it means we're standing at the edge of something enormous, either the greatest discovery in the history of physics, or the revelation that our entire framework for understanding the universe is catastrophically wrong. How we know 95% is missing. Let me start by explaining exactly how we know that 95% of the universe is unknown. Because this isn't speculation. This isn't philosophical hand-waving. This is hard, empirical science based on observations that are impossible to ignore. The story begins in the 1930s with a Swiss astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies about 320 million light-years from Earth. He measured how fast these galaxies were moving relative to each other by looking at their Doppler shifts, the same principle that makes a siren sound different as it approaches and recedes from you. When Zwicky did the calculation, he found something deeply wrong. The galaxies were moving much too fast. According to Newton's laws of gravity, which had been tested and verified for centuries, if you know the mass of a system and the speeds of objects within it, you can determine whether the system is gravitationally bound. It's like spinning a weight on a string. Spin it too fast for the string's strength, and it flies apart. Zwicky's galaxies should have flown apart billions of years ago. The visible mass, all the stars, all the gas, everything we could actually see wasn't nearly enough to hold the cluster together given the speeds he measured. He calculated that there had to be about 400 times more mass than what was visible. 400 times. He called this unseen mass dunkle materie, dark matter. People ignored him for decades because the idea was absurd. 400 times more matter than we can see? Where is it? What's it made of? Zwicky was known for being difficult, argumentative, and generally unpleasant, so it was easy to dismiss his findings as probably a measurement error or a misinterpretation of the data. But then in the 1970s, astronomer Vera Rubin started measuring something different, the rotation curves of spiral galaxies. A spiral galaxy is a disk of stars rotating around a central bulge, like a cosmic whirlpool. The closer you are to the center, the stronger the gravitational pull, so you'd expect inner stars to orbit faster than outer stars. That's how the solar system works. Mercury whips around the sun much faster than Neptune. Rubin measured the orbital speeds of stars at different distances from galactic centers, and what she found was shocking. The stars weren't slowing down as you moved outward. The rotation curves were flat. Stars on the outer edges of galaxies were moving just as fast as stars closer to the center. This is completely impossible if the only mass present is the visible mass, the stars and gas we can see. The only way to explain flat rotation curves is if there's an enormous halo of invisible mass surrounding each galaxy, extending far beyond the visible disk. This invisible mass provides the extra gravitational pull needed to keep the outer stars moving fast. And when you calculate how much invisible mass you need, you get a number that's staggering, roughly 5 to 10 times the visible mass in every galaxy. Rubin measured galaxy after galaxy, hundreds of them, same result every time, flat rotation curves, invisible mass halos. This wasn't a fluke. This wasn't measurement error. This was real. Now you've got two completely independent observations, Zwicky's galaxy clusters and Rubin's rotation curves, both pointing to the same conclusion. There's a huge amount of invisible matter out there. Matter that doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. It only reveals itself through gravity. And it gets better or worse, depending on your perspective. In the 1990s, two teams of astronomers were studying distant supernovae, specifically type Ia supernovae, which are exploding white dwarf stars. These supernovae are useful because they're standard candles. They all have roughly the same intrinsic brightness. So if you measure how bright one appears from Earth, you can calculate how far away it is. The teams were trying to measure the expansion rate of the universe and determine whether it was slowing down. Because it should be slowing down, right? The universe is full of matter, and matter attracts other matter through gravity, so the expansion should be decelerating over time. That's what everyone expected. The supernovae data said otherwise. The distant supernovae were dimmer than expected, which means they're farther away than expected, which means the universe isn't just expanding, it's expanding faster now than it was in the past. The expansion is accelerating. This made absolutely no sense. Acceleration requires a repulsive force, something pushing galaxies apart, overpowering the attractive force of gravity. But what? There's nothing in our understanding of physics that predicts this. The teams checked their data obsessively. They analyzed hundreds of supernovae. They looked for systematic errors. Same result, acceleration, unmistakable, undeniable acceleration. The explanation that fits the data, the only explanation that works, is that there's a form of energy permeating all of space, an energy with negative pressure that creates a repulsive gravitational effect. We call it dark energy, and there's a lot of it. About 68% of the total energy density of the universe is dark energy. So let's add it up. Roughly 27% of the universe is dark matter, the invisible stuff that holds galaxies together. About 68% is dark energy, the mysterious force driving accelerating expansion. That's 95% right there. Everything else, every atom, every star, every galaxy, every planet, every person is roughly 5% of the total. We are a rounding error. The universe is overwhelmingly made of things we don't understand. Now, before you think this is just theoretical speculation, let me emphasize. These measurements have been repeated, refined, and verified by independent teams using different methods for decades. We've mapped the distribution of dark matter using gravitational lensing, the bending of light around massive objects predicted by Einstein's general relativity. We've measured the cosmic microwave background, the afterglow of the Big Bang with exquisite precision. And the patterns in that radiation confirm the 6-8-2-7-5 split. We've studied the large-scale structure of the universe, the distribution of galaxies across billions of light years. And again, it matches what you'd expect if dark matter and dark energy dominate. The evidence is overwhelming. Dark matter and dark energy are real, but we have no idea what they are. Dark matter is probably some kind of particle we've ruled out, ordinary matter, black holes, neutrinos, and a bunch of other candidates. It's something new, something we haven't discovered yet. Physicists have been searching for dark matter particles for decades, building detectors deep underground, smashing particles together in colliders, looking for subtle signals. Nothing. Not one direct detection. Dark energy is even more mysterious. The leading hypothesis is that it's a property of space itself, the cosmological constant that Einstein introduced in 1917 and then called his biggest blunder. But if that's true, we have a catastrophic problem. When you calculate what the vacuum energy should be using quantum field theory, you get an answer that's wrong by 120 orders of magnitude. 120. That's the worst prediction in the history of physics. So either our understanding of quantum field theory is fundamentally broken, or there's some mechanism we don't know about that's suppressing the vacuum energy to the tiny value we observe. This is where we are. 95% of the universe is made of stuff we can't see and don't understand. We've given it names, we've measured its effects, we've confirmed it exists beyond any reasonable doubt, but we don't know what it is. We don't know how it works. We don't know what particles or fields or structures comprise it. And this isn't a small gap in our knowledge. This is a chasm. This is physics telling us very loudly and very clearly that our current theories are incomplete. There's new physics out there, new particles, new forces, new principles, and we're scrambling to find them. Some people find this depressing. We know so little. Physics has failed. but I find it exhilarating because it means we're on the edge of discovery. The universe has handed us a giant mystery, and solving it will require new ideas, new experiments, new ways of thinking. This is what science is supposed to be: confronting the unknown, admitting what we don't know, and working relentlessly to figure it out. The 95% isn't a failure, it's an opportunity. And whoever cracks it, whoever figures out what dark matter and dark energy actually are, is going to revolutionize physics in a way we haven't seen since quantum mechanics and relativity. That's not hyperbole. That's the stakes we're playing for. What dark matter might be, we don't know. Now let me tell you about what we think dark matter might be. And I want to emphasize think, because we're really just educated guessing at this point based on what we've managed to rule out and what our theories suggest might be possible. The most popular candidate is something called a WIMP weakly interacting massive particle. Don't let the acronym fool you. This is serious physics. The idea is that dark matter consists of particles that don't interact via electromagnetism. That's why we can't see them, but do interact via the weak nuclear force and gravity. WIMPs are appealing because they naturally fall out of extensions to the standard model of particle physics, particularly a theory called supersymmetry. Supersymmetry predicts that for every particle we know about electrons, quarks, photons, there's a heavier partner particle. And some of these partner particles would have exactly the right properties to be dark matter. They'd be stable, they wouldn't interact electromagnetically, and if they were produced in the right abundance in the early universe, they'd make up the right amount of dark matter we observe today. It's almost too perfect. The math works out beautifully. The predictions match observations. And for years, physicists were optimistic that we'd detect WIMPs any day now. We built detectors, enormous, sophisticated detectors buried deep underground to shield them from cosmic rays. These detectors are essentially giant blocks of ultra-pure material liquid xenon, germanium crystals, silicon maintained at incredibly low temperatures and monitored with exquisite sensitivity. The idea is that very occasionally, a dark matter particle will collide with an atomic nucleus in the detector, causing a tiny recoil that we can measure. The experiments have been running for years, decades in some cases. They've achieved sensitivities that would make earlier generations of physicists weep with envy. They can detect events with energies equivalent to dropping a grain of sand from a height of 1 millimeter. They've ruled out huge swaths of parameter space masses and interaction strengths where WIMPs could have been hiding. And they found nothing, absolutely nothing. No convincing dark matter signal. The parameter space for WIMPs is shrinking rapidly. If they exist, they're either much lighter, much heavier, or much more weakly interacting than we thought, or they don't exist at all. Another candidate is the axion. This is a very light particle, potentially billions of times lighter than an electron originally proposed to solve a completely different problem in quantum chromodynamics called the strong CP problem. I won't bore you with the details of that, but the key point is that axions, if they exist, would be produced in enormous numbers in the early universe. And even though each individual axion is incredibly light, collectively they could make up all the dark matter. Axions are interesting because they behave very differently from WIMPs. Instead of a few heavy particles, you'd have an enormous swarm of ultralight particles forming a sort of quantum fluid. This fluid would have wave-like properties on certain scales, which could lead to interesting observable effects in the distribution of dark matter in galaxies. We're searching for axions too. The experiments are completely different from WIMP detectors. You typically use strong magnetic fields and sensitive radio receivers, trying to convert axions into photons that you can detect. It's incredibly challenging because the signals would be incredibly weak. But people are trying. So far, nothing conclusive. Then there are sterile neutrinos. We know neutrinos exist. They're particles that barely interact with anything, and trillions of them pass through your body every second from the sun without you noticing. But ordinary neutrinos are too light and too fast-moving to be dark matter. However, there could be heavier cousins, sterile neutrinos, that don't interact via the weak force at all, only through gravity. These could be dark matter. There's also been speculation about primordial black holes formed in the very early universe from density fluctuations, not from stellar collapse. For a while, these were considered a viable dark matter candidate, but observations have mostly ruled them out. We'd see gravitational lensing effects from these black holes, and we don't see nearly enough to account for all the dark matter. The frustrating thing is that all of these candidates are consistent with what we know about dark matter from its gravitational effects. They'd all produce the right rotation curves, the right structure formation, the right gravitational lensing. The effects are all gravitational, and gravity doesn't care about the detailed properties of particles, only their mass and distribution. So we can't use astronomy alone to figure out what dark matter is. We need to catch the particles directly, or create them in particle accelerators, or detect some non-gravitational signal that reveals their nature. And so far, we've failed comprehensively. Now let me talk about dark energy, because this is even weirder. At least with dark matter, we have plausible particle candidates. With dark energy, we're in much deeper trouble. The simplest explanation for dark energy is the cosmological constant, a term that Einstein added to his field equations in 1917 to make the universe static before Hubble discovered cosmic expansion. The cosmological constant represents an energy density of empty space itself. Space, even when it's completely empty, has energy, and that energy creates a repulsive gravitational effect. If the cosmological constant is real, it means the vacuum of space isn't really empty. It's seething with quantum fluctuations, virtual particles popping in and out of existence, and somehow this activity contributes to the energy density of the universe. Quantum field theory predicts that the vacuum should have energy. The problem is, when you calculate how much energy it should have, you get a number that's absolutely enormous. Then you compare that to the observed value of dark energy, and you find they disagree by a factor of about 10 to the power of 120. That's not a small discrepancy. That's 120 orders of magnitude. It's the worst theoretical prediction in the history of science. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in theoretical physics. Either quantum field theory is completely wrong about vacuum energy, which seems unlikely given how well it works for everything else, or there's some unknown mechanism that cancels out almost all of the vacuum energy, leaving just the tiny amount we observe, and we have no idea what that mechanism could be. An alternative to the cosmological constant is something called quintessence, a dynamic field that changes over time and space. Instead of dark energy being a constant property of the vacuum, it would be a field that evolves, potentially even varying in strength in different regions or different epochs. Quintessence models are appealing because they're more flexible than the cosmological constant. They could potentially explain why dark energy seems to be comparable in magnitude to dark matter right now, the so-called cosmic coincidence problem. In a quintessence model, the field could be evolving in such a way that it happens to be comparable to matter density at this particular epoch in cosmic history. But quintessence has its own problems. We'd need to invent a new field with specific properties, fine-tuned to match observations. And we have no independent evidence for such a field. It's essentially adding new ingredients to make the theory work without any deeper explanation for why those ingredients exist or have the properties they do. There's also the possibility that dark energy isn't a substance or field at all, but rather a sign that general relativity breaks down on cosmological scales. Maybe Einstein's equations need modification. Maybe gravity works differently over billions of light years than it does in the solar system. There are modified gravity theories that attempt this FR gravity, where you modify the Einstein-Hilbert action. Scalar tensor theories, massive gravity. All of these try to explain cosmic acceleration without invoking dark energy. The problem is, none of them work as well as general relativity plus dark energy. They might fit the expansion history reasonably well, but they fail when you try to match other observations, structure formation, gravitational lensing, the cosmic microwave background. General relativity with dark energy fits everything. The alternatives fit some things but break on others. So where does that leave us? We've got dark matter, which is probably a particle, but we haven't found it. We've got dark energy, which is either a cosmological constant leading to the worst prediction in physics, or a new field we've never detected, or a sign that gravity needs modification. We're 95% ignorant about the composition of the universe. And the 5% we do understand ordinary matter, governed by the standard model of particle physics and general relativity, is itself incomplete. The standard model doesn't include gravity. General relativity doesn't include quantum mechanics. We don't have a unified theory of quantum gravity. We don't know why the universe has 3 dimensions of space and 1 of time. We don't know why the fundamental constants have the values they do. The more we discover, the more we realize how much we don't know. And that's not a flaw in the scientific method. That's the scientific method working exactly as it should. We're confronting our ignorance honestly, mapping the boundaries of the unknown and working to push those boundaries further. But it's humbling, deeply humbling. We're clever apes on a small planet trying to understand a cosmos that is overwhelmingly composed of things we can't see and don't comprehend. And yet we keep trying, because that's what we do. The cosmic web dark matter's masterpiece. Let me tell you about the cosmic web, because this is where dark matter reveals itself in the most spectacular way. And it's a structure so vast, so intricate, that it makes you realize just how little we actually see when we look at the night sky. When astronomers map the positions of millions of galaxies across the universe, they don't find a random distribution. They find a pattern, a network. Galaxies are arranged in long, thin filaments and sheets with enormous voids in between, like a cosmic sponge or soap bubbles. This structure is called the cosmic web, and it spans the observable universe. The filaments are staggeringly large. Some stretch for hundreds of millions of light years. And where filaments intersect, you get dense clusters of galaxies, thousands of galaxies gravitationally bound together. Between the filaments are the voids, vast regions of space, sometimes hundreds of millions of light years across, containing almost nothing. A handful of small galaxies, if that, mostly empty. Now here's the key thing. The visible galaxies are just tracers. They're like lights on a Christmas tree, marking out the structure but not being the structure itself. The actual structure, the framework of the cosmic web, is dark matter. The filaments are dark matter. The nodes where filaments meet are dominated by dark matter. The voids are empty because dark matter was gravitationally pulled away. We can see this through gravitational lensing. When light from distant galaxies passes through a massive structure, a cluster, a filament, the mass bends space-time, and the light follows the curves. This causes the images of background galaxies to be distorted, stretched into arcs and rings. Einstein predicted this in 1915, and we've been observing it since the 1980s. When you map out the lensing patterns carefully, you can reconstruct where the mass is, not just the visible mass, but all the mass, including dark matter. And what you find is that the dark matter forms smooth halos around galaxy clusters, extending far beyond the visible galaxies. And these halos connect to filaments, which connect to other halos, forming a continuous web of dark matter spanning the cosmos. The images from surveys like the Dark Energy Survey, the Sloan Digital Sky Survey, and the upcoming Vera Rubin Observatory show this structure in breathtaking detail. Millions of galaxies spread across billions of light years, all arranged along invisible threads of dark matter. It's one of the most beautiful things we've discovered about the universe, and most of it is invisible. Now, why does this structure exist? Why did the universe organize itself into a web instead of staying smooth or clumping into isolated islands? The answer goes back to the early universe just after the Big Bang. In the beginning, about 380,000 years after the Big Bang, the universe was extremely smooth. Matter was distributed almost uniformly, with density variations of only about 1 part in 100,000. These tiny fluctuations were imprinted in the cosmic microwave background, and we can still see them today as tiny temperature variations across the sky. Those tiny fluctuations were the seeds of all structure. Regions that were slightly denser than average had slightly stronger gravity, so they attracted more matter. As they accumulated matter, their gravity strengthened, attracting even more matter. This is gravitational instability, a runaway process where the rich get richer. Over billions of years, the slightly overdense regions grew into the filaments and clusters we see today. The underdense regions became voids. The universe evolved from nearly uniform to highly structured, all driven by gravity, amplifying those initial fluctuations. But, and this is crucial, this only works if dark matter exists. Here's why. In the early universe, ordinary matter, protons, electrons, was coupled to photons through electromagnetic interactions. This radiation pressure resisted gravitational collapse. Ordinary matter couldn't start clumping efficiently until the universe cooled enough for atoms to form and decouple from radiation, about 380,000 years after the Big Bang. But dark matter doesn't interact with photons. It doesn't feel radiation pressure. So dark matter started collapsing into structures much earlier, potentially as early as a few thousand years after the Big Bang. By the time ordinary matter decoupled from radiation, dark matter had already formed the gravitational wells, the framework of the cosmic web. Ordinary matter then fell into those wells, forming galaxies within the pre-existing dark matter structure. Without dark matter, the cosmic web wouldn't exist. Structure formation would have started much later, and there wouldn't have been enough time for galaxies, clusters, and filaments to form by the present day. The universe would still be a nearly smooth distribution of hydrogen and helium gas. No stars, no planets, no us. This is one of the most powerful pieces of evidence for dark matter. We can run computer simulations of structure formation starting with the initial conditions from the cosmic microwave background and evolving the universe forward using gravity and hydrodynamics. If we include dark matter, the simulations produce a cosmic web that matches observations almost perfectly. If we leave out dark matter, the simulations fail spectacularly. The structures are wrong. The timing is wrong. Everything is wrong. So dark matter isn't just something we infer from rotation curves or galaxy clusters. It's essential for explaining how the universe got from the smooth initial state we see in the CMB to the highly structured universe we observe today. It's woven into the fabric of cosmic history. Now, you might be wondering, if dark matter is everywhere, if it forms this vast cosmic web, why don't we feel it? Why isn't it affecting us locally here on Earth? The answer is density. Dark matter is spread out. Even in a dark matter halo surrounding a galaxy, the density is incredibly low, less than 1 proton mass worth of dark matter per cubic centimeter. That's essentially vacuum by terrestrial standards. And here in the solar system, far from the galactic center, the dark matter density is even lower. So yes, dark matter is passing through the Earth, through you, right now. But it's so diffuse and interacts so weakly that you'd never notice. That's why direct detection experiments are so difficult. You're trying to catch a particle that almost never collides with anything in a detector that can only see the incredibly rare events when a collision does occur. But on cosmological scales, that diffuse dark matter adds up across billions of light years, across entire galactic halos and filaments. The total mass of dark matter is enormous, 5 times the mass of all ordinary matter in the universe. And that mass shapes everything: the formation of galaxies, the large-scale structure, the evolution of the cosmos. The cosmic web is the most visible manifestation of dark matter's dominance. It's the skeleton of the universe. And we can see the bones, even if we can't see the substance they're made of. This brings us to an interesting philosophical point. For most of human history, we thought seeing is believing. If you can see something, it's real. If you can't see it, it's suspect. Atoms were controversial until we could detect individual atoms. Black holes were speculative until we observed them directly. But dark matter is forcing us to expand our epistemology. We can't see it. We may never see it directly. And yet we know it's real, because we can see its effects so clearly and consistently across so many different observations. We believe in dark matter not because we've detected the particles, but because the gravitational fingerprints are unmistakable. This is the power of indirect evidence in science. You don't need to see something to know it exists. You just need to see the consequences and make sure those consequences can't be explained any other way. And with dark matter, we've checked. We've looked for alternative explanations: modified gravity, measurement errors, unknown astrophysical processes. None of them work. Dark matter is the only explanation that fits all the data. So we're left with a universe that's 95% invisible, structured by forces and substances we don't understand, evolving according to principles we're still trying to figure out. And the cosmic web, that beautiful, intricate, vast network of filaments and voids, is our constant reminder that the universe is stranger and richer than the simple picture we get from looking at the stars. The darkness is real, and it's not empty. It's full of structure, full of matter, full of mystery. We just can't see it yet, but we're working on it. What if we're wrong about everything? Now let me address the elephant in the room. What if we're wrong? What if dark matter and dark energy don't actually exist, and we've been fooling ourselves for decades? What if the whole 95% unknown thing is just a sign that our theories are broken? This is a question that responsible scientists should ask, and some have. There's a long history of alternative theories that try to explain the observations without invoking invisible matter or mysterious energy. Let me tell you about them and why they don't work. The most serious alternative to dark matter is called modified Newtonian dynamics, or MOND. This was proposed by physicist Mordechai Milgrom in 1983. The idea is simple and elegant. Maybe Newton's law of gravity doesn't work quite right at very low accelerations, the kind of accelerations experienced by stars on the outskirts of galaxies. In ordinary Newtonian gravity, force equals mass times acceleration, and gravity falls off as 1 over distance squared. MOND proposes that when accelerations get very small, below a certain threshold, gravity becomes stronger than Newton predicts. Specifically, instead of force being proportional to acceleration, it becomes proportional to the square of acceleration at very low values. This one change, with one adjustable parameter, the acceleration threshold, can explain galaxy rotation curves beautifully. You don't need dark matter halos. The stars on the edge of the galaxy move faster than Newton predicts simply because gravity works differently at those low accelerations. Milgram showed that this fits data for hundreds of galaxies. For a while, this was taken very seriously. Maybe we don't need dark matter. Maybe gravity just works differently on galactic scales. It's an appealing idea because it's economical, one modification to a well-known law, instead of inventing an entirely new form of matter. But MOND has problems, big problems. First, it struggles with galaxy clusters. The same modification that works for individual galaxies doesn't produce enough extra gravity to explain cluster dynamics. You still need about 2 to 3 times more mass than what's visible, even with MOND. Second, MOND completely fails to explain gravitational lensing. When you observe the bending of light around galaxy clusters, the amount of lensing you see requires dark matter, regardless of how you modify gravity. MOND can't produce the observed lensing patterns without adding some dark matter back in. Third, and this is the killer MOND, can't explain the cosmic microwave background or the large-scale structure of the universe. The patterns we see in the CMB, the distribution of galaxies on the largest scales, the timeline of structure formation, all of this requires dark matter as the dominant component driving gravitational collapse in the early universe. MOND offers no mechanism for this. There have been attempts to create relativistic versions of MOND that might work better, like TVIS, tensor vector scalar gravity, developed by Jacob Bekenstein. These are more sophisticated than the original MOND, and they can handle some of the problems. But they introduce new fields and complications, and they still don't match observations as well as standard cosmology with dark matter. So while MOND is an interesting idea, and it does capture some real physics about galactic rotation, it's not a viable replacement for dark matter. At best, it might be pointing to some small modification of gravity that works in conjunction with dark matter. At worst, it's just a mathematical coincidence. Now let's talk about dark energy alternatives. Can we explain cosmic acceleration without invoking mysterious energy? Maybe our observations are wrong. Maybe we're misinterpreting the supernova data. People have looked into this carefully. Could there be dust obscuring distant supernovae, making them appear dimmer and thus farther than they are? No, we'd see reddening of the light, which we don't. Could supernovae in the distant past have been intrinsically dimmer than nearby ones? No, we have independent tests of supernova properties that rule this out. Could there be systematic errors in distance measurements? No, the results have been confirmed using completely different methods, like baryon acoustic oscillations in the cosmic microwave background. The acceleration is real. So if it's not dark energy, what is it? The main alternative is, again, modified gravity. Maybe general relativity breaks down on cosmological scales. Maybe the equations need extra terms that become important over billions of light years. There are many such theories. FR gravity adds higher order curvature terms to the Einstein equations. Scalar tensor theories introduce additional fields that couple to gravity. Massive gravity gives the graviton a small mass, which changes how gravity behaves over very large distances. Some of these theories can produce cosmic acceleration without dark energy. The problem is they have to be incredibly finely tuned. The modifications have to be just right to produce acceleration, but not so large that they conflict with local tests of gravity in the solar system or observations of binary pulsars. And they often predict effects we don't see, like variations in the gravitational constant over time, or differences in how different types of particles experience gravity. Moreover, even if you can make a modified gravity theory fit the expansion history, you still need dark matter to explain structure formation, galaxy rotation curves, and gravitational lensing. You can't kill 2 birds with 1 stone. You need both modifications: modified gravity for dark energy and dark matter for structure, at which point you haven't really simplified anything. You've just replaced one mystery with 2 different modifications. so the alternatives don't work. Or more precisely, they can explain some observations, but they fail when you try to explain everything. Dark matter and dark energy, as unsatisfying as they are, remain the best explanations we have because they work consistently across all observations, from the smallest scales, individual galaxy dynamics, to the largest scales, the cosmic web, the expansion history. This is what makes the situation so frustrating. We know something is missing from our understanding. But every time we try to fix it by modifying our theories instead of adding new components, the modifications don't work. The universe keeps insisting that there's invisible matter and strange energy. We can't wish them away. Now, does this mean we're definitely right about dark matter and dark energy? No. Science doesn't deal in certainties. Maybe there's some completely different explanation we haven't thought of yet. Maybe future observations will overturn the current picture. But any alternative explanation will have to do what dark matter and dark energy currently do: explain rotation curves, cluster dynamics, gravitational lensing, structure formation, the CMB, the expansion history, and a dozen other observations, all with the same underlying framework. That's a high bar. And so far, nothing else clears it. The 95% unknown isn't a sign that we're making things up. It's a sign that the universe is genuinely strange, and our intuitions about how it should work are wrong. We expected a universe made primarily of atoms, governed by gravity and light. We got a universe dominated by invisible matter and repulsive energy. Reality surprised us, and we're still trying to catch up. The hunt continues. Let me tell you about what we're doing to solve the dark matter and dark energy puzzles, because we're not just sitting around being confused. There are massive experimental and observational efforts underway, and some of them are genuinely ingenious. For dark matter, the strategy is three-pronged. First, direct detection, trying to catch dark matter particles as they pass through Earth. Second, indirect detection, looking for signals from dark matter particles annihilating or decaying in space. Third, collider production, trying to create dark matter particles in high-energy particle accelerators. Let me start with direct detection, because these experiments are remarkable feats of engineering. The basic idea is to build an extremely sensitive detector capable of registering the tiny recoil when a dark matter particle collides with an atomic nucleus. We're talking about deposited energies equivalent to a mosquito landing on your arm. Detecting that requires extraordinary sensitivity. The detectors are built deep underground in mines, under mountains, to shield them from cosmic rays that would create false signals. They use materials like liquid xenon or liquid argon, kept at cryogenic temperatures, monitored by arrays of photomultiplier tubes that can detect individual photons. The entire apparatus is surrounded by layers of shielding to block radioactive background. Experiments like Xenon 1T, Lux Zeppelin, and Pandax have pushed sensitivity to incredible levels. They can detect events with energies down to a few keV, kilo electron volts, which is absurdly small. And they've ruled out vast swaths of parameter space where WIMPs could have been hiding. So far, no convincing signal. There have been a few tantalizing hints over the years, excess events that looked like they might be dark matter, but none have held up under scrutiny. The most recent excitement was Xenon 1T, reporting an excess of electronic recoil events in 2020, but further analysis suggested it was probably just contamination. The lack of detection doesn't mean WIMPs don't exist. It means that if they exist, they're either lighter, heavier, or more weakly interacting than the ranges these experiments have covered so far. We're pushing into new parameter space with every upgrade. For axions, the detection strategy is completely different. You use a strong magnetic field inside a microwave cavity. If axions are present, they can convert into photons in the presence of the field. You tune the cavity to resonate at different frequencies, effectively scanning for the axion mass. If you hit the right frequency and axions exist, you'll see a signal, a tiny excess of photons at that particular frequency. Experiments like ADMX, Axion Dark Matter Experiment, have been running for years, slowly scanning through the possible mass range. It's painstaking work because the signal would be incredibly weak, and you have to check each frequency carefully. But they're making progress, ruling out axion masses bit by bit. Indirect detection looks for the products of dark matter annihilation or decay. If dark matter particles collide with each other, which should happen in regions where dark matter is very dense, like the center of the galaxy, they might annihilate, producing gamma rays, neutrinos, or other particles we can detect. Telescopes like the Fermi Gamma Ray Space Telescope have been searching for these signals. There have been some intriguing anomalies, like an excess of gamma rays from the galactic center, but alternative explanations involving astrophysical sources, like pulsars, are also plausible. Nothing definitive. Collider searches at the Large Hadron Collider look for dark matter production in proton-proton collisions. If dark matter particles are light enough and coupled to ordinary matter at all, we might be able to create them by smashing protons together at high energy. The signature would be missing energy and momentum particles carrying away energy invisibly, just like neutrinos do. The LHC has searched for such signals and found nothing beyond standard model predictions. This rules out certain types of dark matter particles, particularly those that would couple strongly to ordinary matter. So direct, indirect, and collider searches have all come up empty so far. Does this mean we're looking in the wrong places? Maybe. Or maybe dark matter is just harder to find than we hoped. The parameter space is enormous. Dark matter particles could have any mass from a tiny fraction of an electron volt to millions of times the mass of a proton. They could interact with ordinary matter at any strength, from fairly strong to almost negligibly weak. We've only explored a small fraction of the possibilities. Now, for dark energy, the approach is different because we can't detect dark energy particles in a lab. Dark energy operates on cosmological scales, so we study it through astronomy. The main strategy is precision cosmology. We measure the expansion history of the universe as accurately as possible, map the growth of cosmic structure over time, and look for any deviations from the simplest cosmological constant model. If dark energy is evolving, or if it's not uniform, or if it's interacting with dark matter or ordinary matter, these effects should show up in the data. Projects like the Dark Energy Survey, the Sloan Digital Sky Survey, and the upcoming Vera Rubin Observatory and Euclid satellite are designed for this. They're mapping millions of galaxies, measuring distances and redshifts with high precision, studying gravitational lensing on massive scales, looking for subtle signals of how dark energy has changed over cosmic history. And they're finding something troubling. There's a discrepancy in measurements of the expansion rate, the Hubble constant. When you measure the Hubble constant from nearby supernovae, you get one value. When you infer it from the cosmic microwave background, assuming standard cosmology, you get a different value. The difference is about 9%, which doesn't sound like much, but it's statistically significant and has persisted across multiple independent measurements. This is called the Hubble tension, and it's one of the biggest unsolved problems in cosmology right now. It could be a sign that our cosmological model is missing something. Maybe dark energy isn't a constant, maybe it's evolving. Maybe there's new physics in the early universe that we're not accounting for. Maybe general relativity needs modification. Or maybe it's just some subtle systematic error we haven't identified yet. We don't know, and that's what makes it exciting and frustrating in equal measure. We're close to something, some inconsistency, some crack in the edifice, and cracks are where new discoveries happen. Another approach is looking for variations in the fundamental constants. If dark energy couples to matter in certain ways, it could cause the fundamental constants like the fine structure constant or the electron mass to vary over time or space. Precision measurements of distant quasar spectra can test this. So far, no confirmed variations, but the searches continue. So here's where we are. We've spent decades searching for dark matter particles and dark energy signals with increasingly sophisticated experiments and observations. We've ruled out many possibilities. We've constrained the properties of dark matter and dark energy to tighter and tighter ranges. But we haven't found the answer. We haven't caught the particles. We haven't pinned down what dark energy is. Some people view this as failure. I view it as progress. Because we're learning what dark matter isn't. We're learning what dark energy doesn't do. We're mapping the boundaries of our ignorance with increasing precision. And eventually, maybe in 5 years, maybe in 50, someone will hit on the right idea, or build the right detector, or make the right observation, and the mystery will crack open. That's how science works. It's not a steady march of triumphs. It's a lot of dead ends, failed experiments, and stubborn mysteries, punctuated by occasional breakthroughs that make it all worthwhile. We're in a long drought right now, but droughts end. And when this one ends, the flood of new knowledge will be spectacular. Why ignorance is beautiful. Let me bring this all together and tell you why the 95% unknown is not just a scientific curiosity, but something that should fundamentally change how you think about reality and our place in it. For most of human history, we've been building an increasingly complete picture of the universe. We figured out the Earth orbits the Sun. We figured out stars are distant suns. We figured out galaxies are vast collections of stars. We figured out atoms, molecules, quantum mechanics, relativity. We mapped the electromagnetic spectrum, discovered particles, understood nuclear fusion. Every generation, we filled in more details, answered more questions. And then in the last few decades, we discovered that we've only been studying 5% of the universe. The other 95% is something completely different, something we can't see, can't touch, can't create in our labs, something that reveals itself only through gravity and then only indirectly. This is not a small correction to our worldview. This is a fundamental rethinking of what the universe is made of. It's as if you spent your whole life thinking you were a biological organism, only to discover that 95% of your cells are something else entirely, something not biological at all, something we have no name for. And the implications are staggering. Every theory we have, quantum field theory, general relativity, particle physics, they all describe the 5%. They are theories of ordinary matter and radiation. They're incomplete. They're missing the most important parts. This means there's new physics out there. Not just refinements or extensions of what we know. Fundamentally, new principles, new particles, new forces, new fields, maybe new dimensions of space we don't have access to, maybe structures and phenomena we haven't even conceptualized yet. Whoever figures this out, whoever discovers what dark matter and dark energy actually are, will have done something comparable to what Einstein did with relativity, or what the founders of quantum mechanics did in the 1920s. They'll have revealed a new layer of reality, and that revelation will almost certainly bring technological and conceptual advances we can't even imagine right now. Think about what happened after quantum mechanics. Within a few decades, we had transistors, lasers, nuclear power, MRI machines, GPS satellites. None of these would exist without understanding quantum physics. The entire modern world is built on quantum mechanics, and quantum mechanics was discovered because physicists in the early 20th century were confronting puzzles in blackbody radiation and atomic spectra that didn't make sense with classical physics. Dark matter and dark energy are our current generation's puzzles, and solving them will almost certainly unlock things we can't predict. Not just cosmology, not just astrophysics, but fundamental physics that could change technology, change how we interact with the universe, change what's possible. But beyond the practical implications, there's something philosophically profound about the 95% unknown. It's a reminder of humility. We're clever. We figured out a lot. We've split atoms, landed on the moon, sequenced genomes, built computers that can beat us at chess and go. We're proud of our accomplishments, and we should be. But we've only been studying 5% of the universe. The vast majority of reality is invisible to us, unknown to us, beyond our current understanding. And that should make us humble. It should make us realize that there are depths to nature we haven't even begun to fathom. It should also make us wonder, what else are we missing? If 95% of the universe's mass energy is something we didn't even know existed until a few decades ago, what else is out there that we haven't noticed yet? What other phenomena, what other structures, what other aspects of reality are we blind to simply because we're not looking in the right way or asking the right questions? This is why I find the 95% exhilarating rather than depressing, because it means the universe is richer, stranger, more surprising than we thought. It means there are discoveries waiting that will astonish us. It means we're not at the end of physics, or even near the end. We're still at the beginning, still figuring out what questions to ask. And this is what science is supposed to be. Not a static body of knowledge, but a process. A method for confronting the unknown, for turning ignorance into understanding, one careful step at a time. We don't know what dark matter is, but we're searching. We don't know what dark energy is, but we're measuring, testing, refining our observations. And maybe we'll never find the answer. Maybe dark matter and dark energy will remain mysterious for centuries. Maybe the particles are so weakly interacting, or the energies required are so high, that we can never detect them directly with any technology we can build. But I don't think so. I think we'll figure it out, because that's what humans do. We're curious, we're persistent. We build better detectors. We come up with cleverer experiments. We think harder about the problem. And eventually, someone has an insight, someone sees a pattern, someone builds the right apparatus, and the mystery cracks open. When that happens, when we finally understand the 95%, it's going to be one of the great moments in human history. not just in the history of science, in the history of thought, the history of understanding. Because we'll have done something almost impossible. We'll have figured out what the universe is made of, even though we can't see it. We'll have used gravity, geometry, mathematics, and careful observation to deduce the nature of invisible substances that dominate the cosmos. We'll have proven that human reason, applied carefully and honestly, can uncover truths about reality that are far beyond our direct sensory experience. That's the promise of science. And that's why the 95% unknown is not a failure. It's an opportunity. The greatest opportunity in physics right now, and whoever seizes it will change the world. I'm 95% sure of that.